Hi. Hello. Thank you for the introduction, and thank you very much to the organizers for inviting me here. And thank you to all the attendees who are here to listen to my talk. So today I will talk about differential privacy in multi-end bandits. Uh, so I'll try to keep the talk a bit general so that people who do not have background in differential privacy or in bandits try to uh, get to understand the basics of at least the both the parts. And later part of the talk, I will give some algorithms uh, for multi-end bandit problem which achieves privacy. So let me now give a small agenda. So at the first part, I will talk about multi-end bandit problem. Uh, I'll talk about two versions. One is finite armed multi-armed bandit, and the second version is linear bandits. Then I will move to differential privacy and give some basics of differential privacy. And the main part of the talk will focus privacy in bandits. First, I will talk private multi-armed bandits, and then I will talk about private linear contextual bandits. I have some additional slides prepared for federated private and federated bandits also. But let's see if we have some time, if I can cover that or not. Okay, let's start. So multi-armed bandits is a problem. It's a learning setting where an agent or a learner learns by experience. So think about it when someone goes to a casino to gamble, right? So there is a big machines you go. There are a lot of handles you can pull, and your objective is to the gambler's objective is to get as many money as possible. But suppose there are 10 handles in the casino. He or the gambler doesn't know which handle to pull, which will fetch him the maximum reward. So what he tries to do? He tries to learn by experience. He pulls some handle. That means he gets to see some action, take some action, pulling some handle, and gets to see some reward, some money he gets, or some losses he suffers. Okay, then now he has some idea. Okay, so this handle, this arm doesn't fetch me good reward. So let me not pull this, pull something else. Okay, say he pulls action 2 and gets some very good gain reward. So he now thinks like, okay, this arm might be good. So let me pull it again. So he pulls again, fetches a huge loss. So now he is confused. Which arms to do? This arm gave me a good reward in the past. Now it is giving me bad reward again. So that means he needs to pull the arms sufficient number of times to get a good idea of the actual reward or actual money he is going to get by pulling that arm. This is what we call by learning as learning by experience. So you always act based on the past data to maximize your reward. And whatever action you're taking now, this will govern how your future rewards are shaped. Because you will take your future actions based on your current rewards that you are getting. So future rewards will depend on present and also the past actions. So as you can see, in this way, in this problem, we get data which is coming to us sequentially. So you take an action, get a reward, take action 2, get reward 2. And the gambler doesn't have any separate budget, or like he cannot fix a separate amount of dollar to purely. Let us now, he cannot think that, okay, let me now just spend $100, just pull all arms 10 times or something and figure out which one is the best one, and then I'll keep on pulling it, because he might end up losing all his $100 based on that. So they're in the environment. And so he needs to balance between explore whether to pull an arm which he has not pulled before to get some information about the arm, or versus exploit. Suppose some of the arms he has pulled already, so he has some idea about the reward of this arm. So let's exploit that knowledge if that arm is fetching him good returns. So all this gambling in a casino that I have mentioned, this can be formed as a multi-armed bandit problem. So let me give some more examples in a machine learning setting. More examples of bandit problems. All right. So say consider recommender system. So you go to a Netflix or IMDb. The Netflix system should recommend you 1 out of n movies. So there are a couple of movies here. All are big, very famous movies. So it has n movies that can be recommended to you, but the system do not know whether you like a movie, right? So which movie the system should recommend to you so that you like that movie, and your like can be expressed by the rating that you give to the movie. Like IMDb has 1 to 10 rating. Suppose you give 9, so that means you like the movie a lot. You give 0, you do not like the movie at all. But the system or the agent doesn't know your history, or so he should recommend out of these n movies. Okay. Let us consider one more example. Clinical trial example. So there are n treatments for a given condition, say diabetes, and some n number of medicines a doctor can prescribe to a patient, but the doctor doesn't know the effects of all of these medicines, right? Whether this medicine will work for this particular patient or not, he doesn't know in advance. So the goal will be to allocate some treatment, which treatment to allocate to that patient, so that the patient gets cured, right? So there are a couple of medicines. These are all the actions the doctor can choose, and based on the responses of the patient to these medicines, that can be the reward the doctor can get. Okay, so with these 2 or 3 motivating examples, let me now formalize multi-arm bandit problem in the next slide. Okay, so multi-arm bandit problem is the simplest RL problem you can think about. RL, we know, you know that there are states. At every state, you take an action, you get to see a reward. Multi-arm bandit problem is the simplest RL problem where there is no state, right? And there are n number of actions that you have to choose from. Say, think about these actions as 1 to n. Each arms or actions have some associated probability distribution on the rewards, but the parameter of the probability distribution is unknown to the agent. Okay, so think about Bernoulli. Arm 1 is associated with the Bernoulli distribution with parameter mu1. Arm 2 is associated with the Bernoulli distribution with parameter mu2. Similarly, arm n is associated with a Bernoulli distribution with parameter mu n. But these are unknown. For example, think about the drugs in the clinical trial of each items, or every movies in the recommender system as items. And the Bernoulli parameters will be whether the drugs work or not, and how much. So recommender system, it won't be Bernoulli, it will be a real value. You can think about a multinomial distribution, but how much rating you will give from 1 to 10. Okay. So how this is how a typical learning goes in multi-arm bandits. Okay, so you are in time 1. Okay, so you select the agent, select arm number 2. Okay, and then it gets to observe a reward y1, which is sampled from the Bernoulli distribution with mean mu2. Okay, this is the reward the agent gets. Say next time it selects arm number 1, and it gets to observe a reward y2, which is sampled from the reward distribution from that arm 1. Similarly, time 3, say select arm number 3 and gets to observe a reward drawn from the distribution of that particular arm. Similarly, it goes on. Time 4, say again arm number 2 has been pulled, and a random reward has been observed from that distribution. All right, so at time t, the game ends, and you get to see a reward from say arm number n. Okay, so this is how the game goes, right? You have a budget of capital T number of rounds. You keep on pulling some arms and get to see some random rewards drawn from that distribution of the arms. Okay, so what is the goal of the agent in this learning game, right? So what are the performance metrics? He or she would like to maximize the total expected reward that she is getting from this total number of capital T rounds. So Y1 is the reward you are getting from at round 1. Y2 is another reward. These are all random samples. So Y2 is the reward you are getting at number 2. Round 2, YT is the reward at round T. So try to maximize the total reward and take an expectation, because all these are random. So take a expectation over the randomness and try to maximize this quantity. This is your goal. Try to select the arms in such a way this quantity is maximized. You can alternatively represent this performance metric as minimizing the cumulative expected regret. That means, what are the loss you suffer due to not knowing the best arm or best handle in the casino, right? You do not know the best handle in the casino. If you would have known the best handle in the casino in the beginning, you would have always pulled that arm, right? So if you pull that arm, you would have always get the best possible reward. For T rounds, you get the maximum reward. So that will be the best possible one you could have got, minus the actual reward that you have gotten, right? So you try to minimize this quantity. You try to be as close to mu max times T as possible. So this expression we call as regret. This is the regret of not knowing the best arm in advance. Okay. So there is another metric that you can also think about, which is the probability of identifying the best action. So you are given a budget of round T. After round T, your goal is to find the best action. Okay, so your goal will be to, okay, there is a round T, I will just keep on pulling arms, and I will try to, at the round number T, I will try to find the best arm, so that after round number T, I can always pull that arm and maximize my reward after that. There are a couple of other metrics, but these three are main metrics that we can think about. By the way, if you have any questions, just let me know. Okay? All right. So let's clinical trial as a bandit problem. Okay. So as I mentioned, okay, so clinical trial we can form as a bandit problem. So what are the arms and what are the rewards we get? So for the TH patient, oh, there's a typo here. It's a TH patient in a clinical study. Okay. So the doctor will choose a treatment, say IT. This IT can be one of these drugs, and observe a Bernoulli response, say whether the patient is healed or not. So the response is either 0 or 1. 0 means it doesn't work, and 1 means it worked. So what is the probability of the treatment worked, condition on the fact that ith treatment has been chosen? So the probability is given by mu y. This is the Bernoulli. This is a parameter of the Bernoulli distribution of the ith drug. And here the goal is maximize the expected number of patients. So there are T rounds, T number of patients are coming. So out of these T rounds, for how many patients the drug worked? Okay, so choose the drug so that number of patients got healed gets maximized. So as you can see, it's a clearly multi-arm bandit problem. So there are n number of drugs you want to choose from and choose the best one so that number of patients get healed. Similarly, we have another example which is recommender systems. So for the TH visitor of our website, the website what it does, it recommends a movie out of this n 5 movies, and observe a reward YT, which is drawn from the reward distribution corresponding to that particular movie, right? So it can be rating. Now YT can vary from 1 to 10, or you can give some kind of continuous rating also. So all things can be captured. So this is the rating, and the goal is to maximize the total number of ratings. So recommend some movies, recommend the best, try to recommend the best movie so that after T rounds, the ratings has been maximized. Okay. Yeah, question?
So what between bandits and just actions in reinforcement learning? Like, for example, if you have a Atari game, can you call right a bandit and moving
Yep.
left a bandit, or
Yeah,
is it different?
Atari game, you are at a particular state always, right? You are in current at a state, then you have a couple of actions to choose from, right? Right or left or up or down, right? So for each state, you can formulate it as a bandit problem. Okay. All right. So let me now talk about one algorithm, one bandit algorithm, which is the possibly the most famous bandit algorithm, which is called upper confidence bound algorithm. So how? Let me talk about how does the algorithm works. So as we do not know, the agent doesn't know the ratings of the items or the reward of the actions. So there is uncertainty on the rewards. So how the agent goes? The idea is to be optimistic where there is any uncertainty. Okay. So we have right. N arms have unknown parameters mu1 to mu_n, which are the unknown reward parameters of the arms. Okay. And the goal is to select recommend an action at every round t to the user. Okay, so what the agent does? First, at every round t, the agent calculates the sample mean of every arm 1 to n. So for arm 1, suppose at round t, you have observed a couple of samples. So you calculate the sample mean and call it as mu1 hat. Similarly, probably you have observed some samples for arm 2, so this is your sample mean mu2 hat. Similarly, you have a sample mean mu1 of hat. So this is the sample mean that the agent computes at every round t. Now consider a case, say arm 2, right? Say it has not been played till round t, right? So you do not have any information about arm 2. So you need to explore, right? You need to get a rule, design a rule which will tell you to explore that arm, because you do not know how much reward you are going to get for arm 2. So that's why you also compute the quantities k1 to kn. What are these quantities k1 to kn? K1 is the number of times you have played arm 1 till round t. K2 is also the number of times you have played arm 2. Similarly, kn is number of times you have played arm n. Now you sum up these two terms. For each arm, you sum up its sample mean mu hats plus some square root of log t time divided by the number of times that arm has been played, ki. You sum up these two terms and you get something, some distribution like this, right? So you have this mu1 hat and say this is mu1 hat plus this square root log t by k1, this red dot. Similarly, for arm 2, you compute this mu2 hat plus square root log t by k2. So you get all these red dots, which are the sum. These red dots are called upper confidence bounds for the arms. So why it is called upper confidence bound? Because you can always take mu1 hat and subtract this same quantity and get a symmetric lower confidence bound also, right? So now, but our goal will be to be optimistic. So we'll take the upper confidence bound to be optimistic. So for every arm, we'll calculate this confidence bound and take the rightmost point of this confidence bounds. And I'll play the arm which has the maximum upper confidence bound. So this is the algorithm. Every round, compute the sample mean, compute that uncertainty, compute the number of times it has been played, and this quantity I will call it uncertainty of that arm, sum it up, and play the arm which has the maximum of this sum. This is the simple algorithm the agent will follow. Okay. Any question here?
Could you maybe explain that log term? How can we understand it in an intuitive way, or maybe how it is derived?
Log term? How I get log term?
Yeah, not how you get, but more like, is there an intuitive way to understand?
Yeah.
Why that
So
is
yeah, the intuition is
concept?
if you scale this square root of log term, right? And obviously we know this, all the arms are independent, right? All the 10 arms in the casino are independent. They are not dependent on each other. So if you take this confidence bound like this, the square root of log t, then it turns out, and you call confidence bound like this, right? Then it will turn out your true parameter, which is mu1 to mu(n), that you have no idea about, will always lie between in this range, in this line, up in this line from here to here, is always lie between with high probability. And the probability will go down exponentially with number of times t. That's why we need the term log t. If you want, with the number of rounds, you want the probability to go down exponentially fast. So this square root of log t term will ensure that.
Thanks.
There's one more question.
So why are we not, in this algorithm, why do we not consider the standard deviation of each draw?
Exactly. You can think about the square root of log t by ki as some kind of standard deviation. Ki is the number of times you have played. Okay. We're not talking about the rewards. Okay. And of course, you're right. Here we have assumed, in this expression, right, we have assumed the rewards are Bernoulli. Okay. Or bounded between 0 to 1. So the square root of ki, 1 by ki, will actually correspond to standard deviation.
Got it, thank you.
Even now, if some rewards are not between 0 to 1, you have to proportionately scale this term to capture the standard deviation. Maybe one more question. Yeah, sure.
So let me try also to draw another comparison of terminology with reinforcement learning, and I apologize if I am understanding it improperly. So in this case, what I am getting is that each arm is some sort of a policy to select the action that I will take at a particular state, right?
Yeah.
Okay, so I have a state, then I choose from the arms, I choose a particular policy, and then from that policy, I take an action. And then
No. The policy will tell which arm to choose.
Okay.
You are in a state. For that state, you determine your policy. The policy is a map from state to actions.
And the actions are the arms?
Actions are the arms.
Okay. So I am confusing then the concept of an arm and a bandit, because...
Bandit is the agent. Bandit is the agent which chooses these actions.
Okay.
You can think about a bandit, right? There are 10 people sits whom the bandit will kill. So all the 10 people are armed for that bandits. He will choose, okay, this guy I will kill. So this is this kind of analogy, bandit analogy. Okay.
Okay, thank you.
Okay, so all right, so based on the previous question, so let me explain why UCB works. So as I've explained already, UCB, because of this UCB rule, this kind of mu I hat plus square root of log t by ki rule, one can always guarantee that this UCB concentrates around the true mean, which is mu I, at an exponential rate. That is probability that the true mean is less than this upper confidence bound mu I hat plus this square root log t by ki, which is always higher than 1 minus 1 by t, right? Now if you can see that, okay, the probability is going down at an exponential rate here. Now how to derive this bound, right? This is a standard Hovding inequality, which works for IID, or independent and identically distributed random variables. Say x1 to xn are some sigma squared sub-Gaussian random variables. You can think about sub-Gaussian random variables which follow a Gaussian law, Gaussian probability law, with variance sigma square. Say x1 to xn are sigma square sub-Gaussian random variables with mean mu. That means expected value of xi is mu, and the moment generating function of the random variable xi is upper bounded by e to the power lambda square sigma square by 2. This is the moment generating function. If you know that this is the moment generating function of Gaussian with 0 mean and variance sigma square. If all the random variables follow this law, then the Hovding inequality tells that for any fixed number of random variables n, the probability that of the sample mean, this 1 by n sum of I2 1 to n xi is the sample mean of the random variable you observe for n rounds. Probability that the sample mean will be close in mu will probability that the difference between sample mean and the true mean will be less than a constant tau. That probability will go down exponentially with the number of points, with the number of data points n. This is the exponential concentration bound given by Hovding, which actually gives that the UCB estimate will always concentrate around the true mean at an exponential rate. So this is the reason why UCB works and converges. Any question at this point?
Hi, I don't fully understand this sub-Gaussianity requirement in this case, and I'm wondering, I'm asking myself, is this an assumption that sometimes holds, sometimes doesn't hold, or?
Sub-Gaussianity is a requirement on the random variables, or the random variable which governs the reward, right?
Yeah.
So for Hovding inequality, we need sub-Gaussian random variables. Okay, and you can think about sub-Gaussian random variables as Gaussian random variables, right? Because this is the moment generating function of Gaussian, so it is upper bounded by the moment generating function of the Gaussian. So any random variable whose moment generating function is upper bounded by the Gaussian moment generating function, it is a sub-Gaussian random variable. So for example, Bernoulli is a sub-Gaussian random variable. You take any random variable bounded between some interval, the support of the random variable, if it is bounded between some real interval, it is a sub-Gaussian random variable.
Okay.
Okay. Think about common examples like binomial, right?
Are there some like adversarial settings that you could formulate that would, I don't know, escape this or break this assumption?
Obviously, there are literature on adversarial bandit where there are some adversary which will corrupt the sub-Gaussian samples by some heavy-tail samples.
Okay.
Then you cannot prove this kind of bounds.
Does that ever happen in like practice, or is
yeah,
that like
it can happen. It can happen in practice, like in financial data, right? You cannot have this sub-Gaussian behavior. It's always a very hectic, very kind of variable behavior. So you cannot give bandit algorithms for that.
I see. Thank you.
Yeah.
So if I understood correctly, mu is the distribution of the rewards that we.
Mu is the true parameter of a Bernoulli distribution. You can think about that.
Okay. Yeah. But so what exactly is the capital X y to an?
Yeah, capital Xi. So mu is a Bernoulli distribution, right? A parameter of the Bernoulli distribution. So you sample n times from that Bernoulli distribution with parameter mu. You observe n samples, x1 to xn, right? These are all the samples, right? And you take an average of that. That is the sample average of mu, right? So this is the sample average, and this is the true mean, true parameter. So this is the difference between sample average and the true parameter. All this bound is telling this two will be close, and the rate that it will deviate from the sample average will deviate from the true parameter will go down exponentially first with the number of examples.
Okay. Okay. Thank you.
Yeah. 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 In this example, there is no t, right? And in this example, t is actually n here. This n here is actually the same as t here. Ki, okay. Sorry. Okay, sorry. Okay. All right. Okay. Okay. This ki is actually n here. In this bound, this number of samples n is actually corresponds to ki for the arm I. Now, for every arm I, you can round this kind of bound, right? And t, you can think about some upper bound on ki for all the ki's. Right? So you get it for for n observations, and you use this bound for all. Right? For arm I, ki, for arm 1, k1 is, you use n equal to k1 to get the bound from arm 1. You use n equal to k2 to get the bound for arm 2. And t, for you take an upper bound on all the k1 to kns. Yeah.
Could you explain this result in terms of exploration versus exploitation?
Exactly.
Why is it tight trade-off? And maybe related or unrelated question, does being optimistic biases us towards exploitation?
No, here, okay. So let me now explain this result with exploration versus exploitation. So the arm, right, which maximizes this quantity. So now suppose for some arm you have this highest sample mean, right? That you have observed couple of points, couple of samples, and you get to see that, okay, this mean is very high. So this rule will tell, okay, play this arm because it's at highest mean, right? But you have the second term also, right? Suppose some arm, this k is very low. That means you have not observed samples from here. So this will tell, okay, this is in the denominator. It will tell, okay, play that also because you have not observed it. So this is the exploitation. You have observation, so exploit it. Second part, you do not have any observation, so exploit it. And what was the second question?
It being tight exploitation, exploration trade-off. I don't understand.
Okay,
that
tight.
at all.
Okay, so tight means you cannot improve over this for sub-Gaussian random variables. This is a tight bound. You cannot improve this bound. Yeah.
So mu unique for each state. It changes for each state.
Yeah, for reinforcement learning problem, you do the same step for each state. You have to do for each state.
Yeah. Okay.
Yeah. Okay. Okay, now let me go to another algorithm. We have talked about UCB algorithm. You can see that all this rule is deterministic, right? You computed this quantity UCB and you are done. You just greedily act upon greedily on this rule. So now how a Bayesian will think, right? Bayesian doesn't want to act deterministically. Bayesian always wants to sample, right? How a Bayesian will think. So what kind of algorithm a Bayesian can propose? So I'm calling this as a fake Bayesian's approach to bandits. Why fake? I'll tell later. Okay, so think about it. Arm 1 and arm 2. Okay, so you put so the rewards for both the arms are between 0 to 1. You can get rewards from between 0 to 1. This is a simplistic example. So Bayesian will put for both the arms mean, right? You do not. Bayesian doesn't have any idea about the mean, so he puts some prior distribution, which is a uniform probability distribution. Okay, so round 1, so it generates 2 random samples from both the distributions. So for arm 1, it gets to see this reward, which is around 0.8. Arm 2, it gets to see this reward, which is around 0.2, right? So this is 2 random samples it generates. Now it will fake by playing the base term, assuming the sample mean is actually the true mean. It doesn't have any information about the sample mean, so it will fake that, okay, I got this sample mean or some kind of sample, so it is the true thing. Okay, so it will play now this arm. Okay, so this mean is 0.8, I will play this one because the other one is 0.2. So I will play this one. So it will play this, right? Now it gets to see the actual reward, right? It gets to see the actual reward of arm 1. So now suppose it sees the reward which is 0.4. Okay, so it gets to see some reward which is 0.4. This is the actual reward. Now what it will do? It has a prior distribution. Now it has some sample. So what the Bayesian will do? He will just update the posterior by using Bayes rule. Okay, now the posterior distribution looks like this because he has observed a sample from here. So this distribution gets skewed here. Obviously, he has not observed any sample from 2, so it is now uniform. Okay, so the next round, it generates again 2 random samples from both the distributions. So here now the most of the probability mass in this region, so it gets a sample from here, say 0.3, and it is again uniform distribution. The sample from 2 is like 0.8. So now it will again fake it, and okay, this thing then okay, this arm is fetching me high reward, so I will play this arm. So it now plays arm number 2. So in this way, it will proceed. So suppose now what it will do, it plays arm number 2 and get to see some kind of reward from say 0.7. So it update the posterior of arm number 2. So after 2 rounds, you have this kind of posterior distribution in hand. Right now, what it will do in the next round, it will just keep on generating samples from both the distribution, compare them, which one is higher, it will play that arm. This is the way he will proceed. This algorithm is called posterior sampling algorithm. It has been proposed by Thomson back in 1933. It has probably the used bandit algorithm in industry. There's a very simple rule, as you can see. Okay, so what a performance guarantee of this UCB and Thomson sampling algorithm looks like. So after T rounds, expected regret of UCB and Thomson sampling both goes only logarithmically with number of rounds T. This is because the exponentially decaying failure probability. That's why it grows only logarithmically with number of T. That means if you divide the total regret at time T by number of rounds, you can get this kind of a curve. It will go down as number of round increases, and asymptotically it will approach 0. So this quantity is order of n log T by delta. N is your number of arms, and delta is your sub. That is the difference between the highest reward minus the second best reward. This is the cumulative regret any UCB and Thomson sampling both suffers. So as T increases, per round regret vanishes. So that means the agent is able to learn the system. All right. Okay. Now let me move to another setting, which is called linear bandits. Till now we have make the assumption that all the arms rewards are independent of each other. But it can be often the case that more structure or coupling is present between the arms rewards. For example, consider this scenario in a 2D plane. There are 5 arms, each, yeah. Okay, delta is the gap between the best arm reward minus and the second best arms reward. So suppose arm number 5 is your best arm, right? So it has a reward parameter, it's a Bernoulli parameter, say mu5, which is say 0.7. And second best arm probably is your arm number 6, right? So it is second best is 0.6. So delta is 0.1. That means you get hit by a factor of 10. Because 0.7 and 0.6 is hard to distinguish from each other, right? It's very close. Now you think about your best arm is 0.7, second best arm is 0.1. So these are very far apart. So you can easily distinguish between these two, right? Your delta is 0.6. So you get hit by a factor of say 1.3 or something. So this is the cumulative regret, and graph I have shown regret by T. Yeah. Yeah, you can think about regret, how it goes down with T. Okay. All right, so I was considering this linear bandit setting where there are 5 arms. Each arm is now a 2D vector, 2-dimensional vector. Each arm sits on this in this plane. So as you can see, all the arms will be related. It's arm 1 and arm 2 are close by, arm 1 and arm 3 are far away, right? So arm I is a vector xi, which sits in a d-dimensional Euclidean plane. Plane gives you a reward theta transpose xit plus some zero mean Gaussian noise. Here theta is some unknown parameter that you want to estimate. Okay, and since the structure, we call it as linear bandit problem. So reward yt is a linear function of the arm given by the weights theta, which is unknown and we want to estimate, plus corrupted by some small Gaussian noise. This is the simplest linear bandit setting we will be considering. Okay, And this obviously this noise is independent of everything. All right. Then what kind of UCB algorithm we can build for this kind of noise? So let's consider UCB for linear bandits. So now our unknown parameter is theta. So we build a UCB estimate for this parameter theta. So how? Okay, so we have this data. We have run this algorithm for t rounds. So we have the data xt and yt. This pair we have. We have played arm xt, get a reward yt. Played another arm xt1, get a reward yt1. So we have this data, and this data follows a linear structure, linear model. So the first thing we can do run a linear regression algorithm and find up least square or ordinary least square estimate, which is theta t hat. Theta t hat can be is your just your least square estimate for the linear regression algorithm. So now we have this point estimate theta t hat, but we now need to also capture the uncertainty of this estimate because we do not have all the data in hand, right? So we need to capture the uncertainty of this estimate. So what do? We build an ellipsoid around this this estimate. So theta t hat is the center, and we build an estimate with appropriate ellipsoid with appropriate radius given by this quantity beta t. This beta t will choose appropriately. So that how the ellipsoid looks like. The ellipsoid will comprise of all such theta such that the distance from theta to the estimate theta t hat under sigma t is upper bounded by beta t. And this Seminorm's matrix sigma t is the sum of S from round 1 to round t, the outer product between the actions chosen for each round. Say xi1 is the action chosen at round 1. So you take the outer product with itself, x1 transpose, and sum it up for t rounds, and it will give you a matrix, right? It will give you a d by d matrix, sigma t. And you compute your distance according to this norm. Okay, this is the, if you know that this is the ellipse, this is actually how one can write an ellipsoid equation in d-dimensional plane. So we're just taking the least square estimate and building an ellipsoid around the estimate. So now we have hand, right? So let us call this ellipsoid as CT. So what we will do, the UCB. UCB is always optimistic. Yeah.
Could you please quickly explain how do you use this matrix to calculate the distance?
Sorry?
How do you use that matrix to calculate the distance?
So this quantity you know, right? Theta minus theta t hat of sigma t. Right? It is a weighted Euclidean norm. Right? What is this? Theta. So x is your vector. M is your matrix. Norm of x under M square is x transpose mx. Okay?
Right, thanks.
Okay, so we have this ellipsoid. So an UCB will always go with the most optimistic option. So what UCB will do? UCB will play the most optimistic action with respect to this ellipsoid. That means, so for each arm I, the UCB algorithm will compute this quantity, max of theta transpose of xi. So this is an inner product it can compute. Now say it can also compute this maximum. This is a maximum over an ellipsoid. Say suppose we can also compute this. So you can compute for each arm I. Now play the arm which has this highest quantity. So this is a simple rule that you will do, right? And it turns out that this maximizer is easy to compute for an ellipsoid. Okay, there is a closed form solution because the ellipsoid has a particular form like this. So there is a closed form solution of this maximizer. I'll talk about it later. Okay. So now I have talked about UCB algorithm. And so what about Thompson sampling for this algorithm? How a Bayesian will think for linear bandits? Okay, so this is Thompson sampling or posterior sampling for linear bandits. So we have the same least square estimate that I have computed for lean UCB, theta t hat. Now instead of computing this ellipsoid, Thompson sampling will construct the multivariate Gaussian distribution. So to construct a multivariate Gaussian distribution, you need a mean vector, which is theta t hat. And also you need a covariance matrix, right? So this sigma t, that you have computed this matrix sigma t. You take the inverse of it and take it as your covariance matrix. So this will be your multivariate Gaussian distribution. So at each round, we can compute this multivariate Gaussian, and then we can also sample from it. So Thomson sampling algorithm will sample a theta t tilde from this multivariate Gaussian distribution. So now sample point estimate theta t tilde. Okay, and this also takes care of this sampling from a Gaussian distribution will takes care of your exploration. And since you are sampling with this mean, it takes care of your exploitation. All right. So now I can just act greedily with respect to this sample parameter. That means choose the arm I, which maximizes this theta t tilde transpose xi. You're just acting greedily with respect to the sample parameter. So this arm Thomson sampling will choose every time. And the good thing is there is no need to optimize over an ellipsoid. The sampling will takes care of everything. Or to take any question. Okay, so if not, I will move to the main topic, bandits through the lens of differential privacy. Now I will introduce some differential privacy basics. So let us now recap our multi-arm bandit problem with this add recommendation example. So we have several users, which if a user will come to the recommender system. So round T, some user comes, T plus 1 another user comes, T2, T plus 2 another user comes. So each were recommended some ads, right? So first user recommended green ad, second one also the same green ad, third one yellow ad. The user gives some response, okay, he is happy or she is happy, or she gives 1 rating. Next user also happy with the, no, he's sad with the green one. The third user also sad with the yellow one. So add is your action, these smileys or sad faces are your rewards. And this will server, right? So when you give your response, it will ultimately go to the server where all the computation is taking place, right? That means you can think about the server is computing all your UCB Thomson sampling things. All the estimates are being computed in the server. So you pass to the server. All the users will pass their data to the server. All right, the server gets 2 reward, 1 is good, 1 is bad. Yellow ad 1 reward, okay? So it computes a model about the problem. You can think about this model are your UCB estimates. Okay. Now this model it transfers to the next user that comes, right? So this another user comes. So this model is there, and sorry, what happens? Okay, so this model gets transferred here, right? And this model will be used to recommend this kind of this red ad to the user. So what is our rewards? So green ad has some reward mu1, yellow ad mu2, and blue ad mu(n). So these are all your n possible ads or actions. So this is the regret expression that I have talked. All right. So where were we? We had this in model. So model was given to the new user, and the model or the UCB has recommended this ad to choose for this user. Okay. Now the thing about these rewards can reveal some personal information. Like suppose some ads were shown to me, I liked it, it will reveal some kind of my personal preference, my gender, right, something, which I do not want to reveal to anyone else. So this is my sensitive information. I do not want anyone to know about that. I want it to be private. However, since my preferences or my rewards has been used to compute this model, and based on this model, a new ad was recommended to a new user. Now, if that user is suppose some adversary, he is someone of malicious nature, he can know that okay, so this ad has been recommended to me, but it has been computed within this model. So he can infer some information about the rewards of other users. Okay, because some kind of ad has been recommended to him based on some model which has been computed with other person's rewards. So if he is an adversary, he can use this information to infer some rewards. Or if some external attack happens in the model side, the external agent can also infer this kind of information. So we want to build up UCB or build a bandit algorithm which doesn't reveal this kind of information, this kind of sensitive or private information. Okay, so this will be the goal. Let's formally introduce differential privacy. So differential privacy is a class of algorithms which facilitates computing and releasing some statistics from sensitive and private data, and ensure that privacy is not compromised. So we have a pool of private data. Think about all the rewards of a lot of users in the recommender systems. A differentially private algorithm makes some aggregate statistics. Think about all the aggregate statistics are your UCB estimates. And this aggregate statistics has to be noisy. Why noisy? This noise or randomness should conceal the contribution of individual users. You need to put noise in such a way that individual users' sensitive information gets concealed in the aggregate statistics. The UCBs will not give away sensitive information or the reward of some particular user. In this way, we need to build some UCB estimates. So that these estimates now can be safely handed to an all-powerful adversary with no risk of a privacy leakage. Okay. How will you select this noise? The noise should depend on the sensitivity of the output. That means how much the output change if we change one single input data. That means if we change one single user, how much the UCB or how much the final action that gets recommended to another user changes. If it doesn't change that much, that means it will not reveal info about that particular user which you have replaced. Okay, so DP has been introduced by Dwork in 2006, and since then she has received numerous prizes, including all the possible theoretical computer science prizes you can think of. She has received. The other thing, the Turing Award, she may receive in a couple of years. So, okay, so let me now give the definition of DP. A mechanism, you can think about an algorithm here. We just add some noise to the data. M is called to be epsilon differentially private if for all pair of data set D and D prime that differs only in the data of one single user. So if there are n points in both the data sets, n minus 1 users data points are same, you just change one, okay? Such that for all possible outcomes of that algorithm, the probability of output belongs to some set E is upper bounded by e to the power epsilon times probability of output when the input is D prime belongs to the same set E. As you can see that the two outputs will be bounded by this quantity e to the power epsilon. And okay, this probability is getting introduced by the randomness in M. And e to the power epsilon is the amount of privacy loss that you are willing to suffer, or amount of privacy loss that you are willing to suffer. Okay, this much of privacy loss I am willing to suffer. Okay, now in some cases what will happen, this expression, this equation doesn't hold almost surely, it doesn't hold always. Then we can introduce some kind of small slack. Suppose with some probability it doesn't hold. But this probability, we would like to ensure this kind of equation hold in that case, where delta is a very small quantity. It's a failure probability that the privacy guarantee, we are not able to give privacy guarantee. Right? With this failure probability delta, small failure probability delta, we won't be able to give the guarantee. Now some properties of DP. DP is post-processing. DP holds in post-processing. That means suppose you may ensure that your algorithm gives privacy. Now downstream task you perform after that, it will always be private. Okay, whatever. So that is the post-processing property of DP. That means it is future proof. So you do make sure your algorithm is private, then everything is future proof. Also suppose you have two different private mechanisms working one top of another, right? Then you can compose these two mechanisms and give a composition of these two functions. And then what will happen, this epsilon and deltas will just add up. I mean, two mechanisms each having privacy loss epsilon, so it will be, the composite mechanism will have only privacy loss 2 epsilon. Okay, so these simple properties which will be very helpful for us. Okay. Okay, let us now zoom in a bit. See, data is collected from different users. So we have expose the general trends. Okay, this is the trend the data is following, but we will protect the individual privacy of the users. That is the goal of building a DP algorithm. So it has been by Apple in 2015 in iOS telemetry task. They used epsilon equal to 8. Okay, and obviously you can see that parameter epsilon is the privacy budget and accuracy. So you added some noise to make your algorithm private, but you will suffer some drop in accuracy. And accuracy drop with epsilon goes like this. So this accuracy drop is the e to the power epsilon term, right? So if epsilon is 0.5, your adversary advantage or drop in accuracy is 1.6. That is okay, probably doable. Epsilon is 1 is 2.7 doable. Epsilon is 8, which Apple used 2,824. Maybe probably no accuracy gets dropped by anything, right? But epsilon 20 some 456 million or something, some big number. So there's no point of putting epsilon equal to 20 if your accuracy gets suffered so much. So we need to make sure as possible. When we build our algorithm, we need to make sure epsilon is very small. Epsilon 20 doesn't make sense. However, US census in 2020 used epsilon equal to 19.61. So accuracy gets hampered, but their data is protected. In US census data probably accuracy doesn't matter. They just want to protect information of people. So for them, it makes sense. But for algorithm, this kind of high value of epsilon doesn't make sense. We need epsilon to be as close to 1 as possible or 0 as possible. Also, one very important aspect in DP is the view of adversary, like where the adversary can attack. Can the adversary attack in the server, or can the adversary attack in the local side also, right? So I'm a user, I am using a mobile app to send my thing. If an attack can happen in my mobile app also, or the attack can happen only in the server where the computations are taking place. So these kind of models are very, view of adversary is very important to devise different differentially private algorithms. I will explain in a detail later. Any question at this point? Okay. All right. So, okay, now I talked about the view of adversary is very important. So first is the central model of differential privacy, where we trust the central server, where all the UCB computations, everything is taking place. I trust, the users trust that the server. Okay. Okay, so this ads has been recommended to the users. It has given the rewards, and user sends all their raw data, the ads recommended to him, and their rewards to the server directly. It trusts the server blindly, it sends it to them, sends it to the server. Now, the server has a job. Server's job is to, when it computes this model or this UCB estimates or anything, like whatever computation it does, it needs to make sure that each of the model updates is differentially private. Because then if an attack happens here, so the adversary cannot guess which the user's private information. So it needs to make sure whatever computation it do, it is differentially private. And obviously, we have talked about post-processing of DP. So once this model is differentially private, whatever you do after that, it's also differentially private. Yeah.
I have a question about that inequality up there. So M is a mechanism, so it could be in the context of machine learning our model class, and D is our data set, and outcome, I believe, could be a certain instantiation of a machine learning model. And then we compare two different data sets, then it sounds to me that it's a measure of variance. Is it the case, or how is it different than?
It's not a measure of variance. So data set varies in only one entry. you compute your model, you train your machine learning model with these two, right? You get some training loss, right, for both the models. So M of D, you can think about training loss when trained with D and train with D prime, right? So it is, this equation is just telling, just think about delta equal to 0 as of now. No failure probability, we are very good. So now divide by this. So probability of MD belongs to E by divide by probability of MD prime belongs to E. Take a logarithmic. So log of this thing is less than epsilon. So this log of this quantity is called privacy loss. So, okay.
So it seems to me that if we add, let's say, strong enough bias to our model class, then we guarantee that the ratio is going to be, epsilon is going to be very low.
Strong enough?
Bias to our model class, because then it's not going to change.
It doesn't have to, so if you add strong enough bias in the model class, you have to do it in both the time. When you are training with D and you are training with D prime. For both the cases, you need to do. Even if you do that, you need to make your model in such a way that this ratio is maintained, if you want to guarantee differential privacy. Does that answer your question?
Okay.
See, you can think about, okay, bias as a noise, right? You can think about bias as a noise, and you select your bias as which depends on epsilon. Okay, then you can also guarantee this. This will also become DP.
Okay. Okay. Thanks.
Okay, I was wondering how practical such an attack could be. So if the model was trained on so many individuals, was there ever an attack or something that could actually gain some valuable information about some individuals? Or
Yeah. There could be a lot of data reconstruction attack. Okay, so there are some particular type of data reconstruction attack. I won't go to the details, which can attack when you are, so you have trained a model, right? You have trained a, say, neural network, you have trained some weights. You can attack in the weights, and you can reconstruct the exact data which is missing from D and D prime. There are attacks in the literature people have proposed.
all right, thank you.
All right. Okay, one more question. One more question. I think.
Yeah, so maybe just let me follow up on this question. So in order to do an attack, what an attacker needs to actually obtain, like just one model and kind of know something about this particular user, or or the attacker needs to obtain somehow two models and kind of like compare them somehow, or like
Yeah, attacker can, what the attacker can do, if the attacker has access to the whole database in some general, it can randomly leave something out, some data point out, and do the training himself. The attacker can be all powerful, do the training himself to reconstruct all this. This kind of attacks are also there in the literature.
Okay, thank you.
How do you make sure that each update is differentially private?
Each update?
Ensure that each model update is DP?
Yeah, so when we do this UCB computation, right? Or what do we need for UCB computation? We need the sample mean, right? When we compute the sample means, we make sure each sample mean is DP by adding some noise, some appropriate noise.
Okay, got it.
I'll talk about this later.
So from the definition up there, the concept of being differentially private is related to the stability of the algorithm. Because when I say stability, I mean if you train your model on some data set and you slightly change data set, the model doesn't change too much.
Yeah, exactly.
And there's some links that stable models are also linked to generalizing well.
Yeah.
Does that mean that if you build models, machine learning models that generalize well, then you're also likely to be better in terms of privacy?
That's a nice, good question. I don't know if there are any result which proves that DP implies stability or stability implies DP. I don't think there is any result, formal result. But people tends to think that, okay, if you ensure DP, and that means one data point changes, your output doesn't change, your algorithm is stable, right? But there is no, that one implies another and vice versa. I'm not aware of this.
Thank you.
Okay. Okay, let us now recap UCB. How do you do differentially private UCB? Right? We need to make UCB estimates are differentially private. Someone asked this question, that how you make every model update is differentially private. So when you compute this UCBs and you compute the sample means, right? That time when you are computing sample means mu I hat, you add some kind of noise to the observed rewards to compute this noisy means. You compute some noisy sample means. So what kind of noise we can add, right? So you have the sample means, and you can add a part of the sample means with some Laplace noise. This is the probability distribution function of Laplace. This is given by this formula. What we will do in our algorithm, we'll put this mu equal to 0. That means 0 mean Laplace. And the shape parameter, right? This is a scale parameter of Laplace B. We'll tune this scale parameter with respect to the privacy budget epsilon. All right, so B will be S by epsilon, and S is the sensitivity. That means how much the data changes if you change one user's data. And if it is a Bernoulli reward, it's just changed by 1, at max 1, right? 0 to 1. So it's, B will be 1 by epsilon. So I will add noise, which is drawn independently from this distribution, Laplace 0, 1 by epsilon, and add this with the sample mean. Okay, and that I will take here and add the variance correction term, and that will be my differentially private UCB estimator. And this will prove, and Laplace mechanism is differentially private, we can prove it. And so by post-processing property, our UCB estimate is also differentially private, and whatever we do will be differentially private. So yeah, so there is an algorithm proposed by Sajed and Shefe. They take this UCB algorithm and log T Laplace noise at the server. So you have T capital T total number of rounds. And they have shown that, okay, since we are adding noise only at the server, so we can only need log T number of noise. So if you need to know how this log T comes, I can discuss it later offline. But you can think that, okay, there are some intelligent binary tree-based scheme. So you have T number of data points. You can put all the T number of data points in a binary tree, right? And whatever whenever suppose you get to at round 4, you need to get some private UCB estimates. So you only need to calculate 2 noise, right? Log 2 of 4 is 2, right? So you only need to calculate two noises to get 4 differentially private UCB estimates. So for T rounds, you get only log T number of noise. And this algorithm achieves pure DP. And what is the privacy cost? Cost of privacy it pays. The cost of privacy is order of n log T by epsilon. So you can see that if epsilon is small, that means your regret is cost is high. And epsilon small means we wanted epsilon to be small, right? Epsilon small means our privacy is higher, right? And your regret will get suffered, right? But if epsilon is high, your regret will not get suffered that much, but your privacy will be lower. So this kind of privacy accuracy trade-off will get. But it is not that bad, so because this guarantee will hold for any epsilon between 0 to 1, right? So it is not that we need epsilon to be greater than some 10 or something. It will hold for any epsilon. So the practitioner will have a choice what epsilon to choose. Okay. So now let us consider another privacy model. Okay, so here is additive cost, which is the local model. So I've told you that the view of the adversary is very, very important, right? So previously we have considered the server which is trusted. Now let us consider the case where the server is not trusted. That means the user do not trust the server. Where all the computation is taking place, he doesn't trust that server. Okay. This is called the local model of differential privacy. All right, here are all the users. He or she doesn't trust the server. That means the attack can happen at the mobile device of the users, right? Attack can happen there. Okay, so he cannot just send his raw data to the server because the adversary can observe the user's output directly. You can think about the server is itself the adversary, so you cannot trust it. So he can, if you send a raw data, the server can see it. Okay, so the key here is to ensure that each user's output, whenever an user sends his raw data, it will make sure its output is differentially private. So that whatever happens in the server side after that remains differentially private because of the post-processing. All right. So in this model, each user needs to make sure whatever he or she sends is differentially private. So how every user does that? Same Laplace noise. So take his own data and add a Laplace noise with his own data. All right. So Laplace noise is generated from this distribution. Laplace mu is 0, b is 1 by epsilon because sensitivity is 1. Each user takes its own reward, which is either 0 or 1 in Bernoulli. Right? Suppose it's 1. Then samples the Laplace noise or Laplace samples random sample from this distribution, Laplace distribution with mean 0 and shape parameter 1 by epsilon. Suppose it gets something like 0.2 and just add it with that and send it to the server. Okay. In this way, each user makes sure that his or her output is dp. So whatever computation it takes place here, it's also dp. So this paper does that. It uses UCB and T Laplace noise. Why T? There are capital T number of users. Each user will need to add one noise. So it gets this kind of algorithm. Okay, yeah.
So we were giving reward in a range from 1 to 0 to 1,
yeah.
Right? So, but like, how much in like safe can this information be if there is such a slight change to what the user feedback is?
Yeah, suppose the reward is 0, right? And some 0.1 kind of Laplace has come, right? Yeah, you're trying to quantify it, right?
Yeah, I mean, like, if it's 0.1, I think that the adversary could derive the fact that it's more likely that the user actually gave a negative.
Yeah, but the user will be, it's not that one sample, right? There will be other samples, right? That samples can come base 1, right? That will also be, this 0 reward can happen multiple times. And the Laplace randomness, it's not that it will always be 0.1. It will be sometimes 0.7, some 0.5, and a lot of samples will come, right? So it will be hard for the adversary to guess it.
Oh, okay. Okay, thank you.
It's not one sample. There are multiple samples.
So, like, is there like a particular reason or intuition why it's Laplace?
No, it's not. It's just an example. I'm just talking about an example. It can be Gaussian. There's no particular reason. But you need some distribution which has nice concentration property, like kind of Gaussian is a good concentration property. Laplace also have good concentration property. You cannot perturb it with some distribution which doesn't converge. It doesn't have a light tail. If it is a heavy tail, very big and fat heavy tail, it will be hard to get the accuracy right. It will suffer because you are adding a heavy tail noise, right? It will suffer the accuracy of the algorithm. Okay. This is the algorithm, and the cost is a multiplicative term, right? You get hit by a multiplicative term of 1 by epsilon square because you are adding so much noise, capital T number of noise you are adding, so you get hit by a lot. But this is the price you pay if you want to protect information at the user side. Okay, you are adding so much noise, you will get hit by the accuracy. Okay, so this cost is no multiplicative. Okay, so the summary is in the central model, the privacy protection level is weaker because you trust the server, so your accuracy doesn't get hit by a lot. In local model, your privacy protection is stronger because you're protecting the local data, so your accuracy doesn't get hit by a lot. So let us try to find a sweet spot between these two. So you will doesn't get hit by that much of accuracy, but your privacy will not be that weaker as a central model. That means you still have a untrusted central server, but you will still get a better additive privacy cost. Let's try to find this sweet spot. This is called distributed model. Okay. All right, this is all these users and all the ads. So now central server is still untrusted, so an adversary is sitting there. But we will assume there is a secure protocol an engineer will implement, which is secure. No one can breach this. This is the assumption we'll make, right? This has been implemented by Apple and all. They have implemented this kind of secure protocol in their pipelines. So this kind of engineering things already is there. So we'll try to use this in our bandit algorithm and try to prove some performance bounds with this differentially privacy guarantee and regret guarantee with this secure protocol, because it has already been implemented by Apple for 4 or 5 years. So users doesn't trust the server, but it trusts this third party, which is a secure protocol. Okay, so this is the model here. So now the key, the output is differentially private. The users doesn't have to protect their, make their own output differentially private anymore, but it needs to ensure that the output of the third party is differentially private, because then if the untrusted and an attack happens in the server, it doesn't reveal any personal information. Okay. So how we're going to achieve it? Okay. So each user have their own data x1 to xn, right? And each user, what it will do, it will apply some kind of function, randomizing function R to their data. I will talk about it later. Okay. Each user will apply this kind of data and send it to the secure aggregation function, which are y1 to yn. What does this secure aggregation function does? It takes this y1 to yn as input from all the users and output a modulo sum of that inputs, which is sum of yi, I varies from 1 to n, mod, which is like modular division by some number m. Okay, this is the secure aggregation protocol does. It just does this kind of computation. Okay. However, this alone does not provide formal privacy guarantee, because we need to ensure add some kind of noise to mask the user's output, right? Now think about randomizer, add some kind of noise on the reward. Okay, but however, all the output of the noise needs to go to the secure aggregation protocol, right? And secure aggregation does this modular division. And modular division you can perform only on discrete numbers, right? You cannot perform on continuous values. You can perform only on discrete values. But how continuous values, and if some kind of small noise or something is added here, this will also be continuous. So before passing it, we need to make sure this function R, whatever it passes, that y1 to yn, it needs to make sure y1 to yn is a discrete value, so that it can be passed to secure aggregation and all the computation can be, this kind of modular division can take place here. So you need to make sure this y1 to yn is discrete. Okay. So make sure whatever noise it adds, it needs to be generated from a discrete distribution. It has to have support in the line of integers. Okay, and suppose all this y hat has been computed by secure aggregation, and it now passed to the central server where all the UCB computation will take place. So A is a function I denote which does all these UCB kind of computations. Okay, so say y hat and A is and say z is the output of y hat. So z equal to A of y hat. We need to design a in such a way that z is approximately equal to sum of xi's, because when we are doing this R, we are adding all these kind of discrete noise and all, right? We have all these continuous values. We need to discretize it, add some noise, and ultimately what we are doing, we are taking a sum, right? And here also the modular operation is taking place. All this discretization and modular operation will introduce a lot of error, and this error needs to be taken care of in this function. You need to de-errorize this, right? Whatever error has been crept up, you need to just make sure you have removed all this when you compute this. So all these things needs to be made sure, so that we can get an unbiased estimate of the sum of xi's as a final output z. That means final output z is very close to the sum of xi's, right? That we need to make sure all in this R function and A function. We do not have any control over the secret aggregation. It has already been done. It has been fixed. Okay. So now with this, let us now give an algorithm which will achieve this distributed differential privacy and also give us good regret bound. Okay, we consider one algorithm which is a variant of UCB algorithm. It's very related to UCB algorithm, but it's not exactly UCB. It is called arm elimination. Okay, it will batches of some fixed sizes, and after every batch ends, it will eliminate some bad actions. Okay, after one batch end, it figure out, okay, these couple of actions are not good, I will just eliminate it. And it will stop when there are only one action left. So that is the best action. It has found the best action, so it will just stop. All right. So suppose we are at some kind of batch B, and the batch size we will fix L of B is 2 to the power B. Batch size just doubles after every batch. So first batch is 2, second batch is 4, next batch is 8, then 16, and it will go on like in doubling intervals. So first batch there are 2 users. Okay, 2 users are here. There is a current model, current estimate of some initial model, green. The model to the users, get these 2 data, either liked it or not. Okay. These are your x1, x's, x1 to x1 and x2, and user adds some kind of randomizer function R, which gives y1 to y2, and make sure y1 to y2 are discrete quantities, discrete values. Okay, this is the first batch, 2 to the power b, and okay, so in the batch there are two active actions, green and yellow. So green action has been recommended, and this kind of rewards has been observed. Okay, so now it has been passed to secure aggregation, and secure aggregation does this modular operation there. Now we have to do this for the yellow action also, right? So same, there are 2 users. Yellow action has been prescribed to them. Some rewards has been observed. The function R operated on that rewards, make it discrete, add some noise, pass to the secure aggregation. Okay, secure aggregation has been done, and there are now. We are here, right? It has been passed to secure aggregation. Now we have to update the model, right? So for both the ads, we compute the sample mean for both the ads, right? We have observed some rewards, and we have computed the sample mean for both the ad, green ad and yellow ad. So now we figured out that, okay, yellow ad sample mean is very less. Okay, so now take the green ad only. So we eliminate the yellow ad, now we will take the green ad. So green ad will be an after the elimination. Okay, so we now have only one ad left. In this example, there can be multiple ads, obviously. So in the next batch size doubled, 4 users, all recommended to him, to the users. Some wise x1 to x4 the rewards are observed, and the rewards are in added noise and discretized to y1 to y4, passed through secure aggregation protocol. All right. And the computation goes in this way till how long it will go? Till when we have only one ad left. In this example, obviously I have shown only one ad left, but you can think about there can be multiple ads. You stop when there are only one ad left. Okay, so let me now give the randomizer function and analyzer function. How does R looks like and how does A looks like? Okay, local randomizer R, it needs to do 2 things. It needs to make all the x's, xi's discretized, and it needs to add some kind of noise to randomize, right? So you take xi and do some kind of, which is called randomized rounding, multiply with by some parameter g, take the floor of it, right? Xig of floor of it, get some value, and take the error, whatever the floor has been cut off, take the error and sample a Bernoulli random variable from that distribution, and add both this, and you get some xi hat. This is the discretization procedure. Now we have xi hat, you have to add some noise. We add some noise in eta I, which has to be a discrete noise because xi hat is discrete, and take sum with xi hat and do a modulo clipping with some parameter m and get yi. This is the R function looks like. You can think about some kind of computation is going on. For every user, we'll just do this, right? I'll tell to add this eta I noise. This has not been told. So yi's have been computed, passed to secure aggregation. Modular clipping has been done in secure aggregation, and now we are in the analyzer. This modular clipping has been done for all yi's. This all yi's comes here, and this computation takes place here. And we are in the analyzer. So analyzer have this y hat as input. So what it needs to do? It needs to do whatever error has been crept up in these steps, right? Some kind of randomized, whatever error has been crept up, it needs to de-errorize of everything. So what it does, it performs this kind of operation. If y hat is greater than some kind of threshold, it just take this z equal to y hat minus this m by g, and else this. So you can think it as a black box function, which can be done for all possible y hats. Right? It just makes sure that all the errors which has been crept up for discrete region has been de-errorized. All right, too much of mathematics. So now how noise, right? So this is only one bit left. Okay, so we need to add some privacy noise eta I to each input, and it has to be a discrete random variable. So what we will do? We'll simulate a noise from the discrete Laplace distribution. So discrete Laplace distribution has PMF of this form. It is similar as continuous Laplace distribution, but a specific form. All right. So now there is no Python package in NumPy or SciPy which can simulate it for you. At least I do not know. So how to simulate discrete Laplace in computer? For that, we generate another random variable which is called Polier random variable, which you can think about negative binomial. A negative binomial you can sample in Python. So how does Polier random variable, which takes the PMF in this form, you can think that it looks like binomial distribution, right, with parameter beta. It is a negative binomial distribution. So you generate 2n IID samples from this Polier distribution with the specific parameters 1 by n or something. These 2n IID samples you generate, you can sample it in Python. And then take sum of I equal to 1 to n, gamma I plus and gamma I minus. And you can prove that this total quantity, this random variable is distributed as discrete Laplace. So in this way, you can simulate discrete Laplace in finite computers. All right. So eta I will be, our eta I will be this quantity, sum of I equal to 1 to n, gamma I plus minus gamma I minus. And we'll add this eta I to every xi. And we can prove that privacy, that we can get differential privacy. After doing all this computation, we'll prove that we'll get differential privacy. And the regret is order of only n log t by epsilon, which is the sweet spot we are aiming for. So for that, we need to do all these things, and ultimately we achieve this. Okay, any question? Maybe I bored all of you. So, okay. And it's already the end of the day. I will not bore you again, and I'll talk about that the same thing you can do for linear contextual bandits. Let me just motivate it and just stop it there without giving any details. Take that linear contextual bandit problem. You have user's context city, prescribe. Context can be your age, gender, medical history. These are all sensitive information. Some action, some medical medicine has been recommended to you, and some kind of linear reward you observe. Okay, and you have to, this is the cumulative regret you want to minimize. This is the linear model that I have talked about, right? What is the privacy concern here? Both the context and reward. Context is your medical history, gender, everything is sensitive information. And also reward. The prescribed medicine worked for you or not. It's a sensitive information. Let's say this example, Bob has some medical history. He has diabetes. And he uses some health app which often prescribes him this black medicine, right? And we do not know whether he's happy or not. Now suppose a new user comes, Alice, and she also has diabetes. And the app prescribes her this green medicine, and she is extremely happy with that medicine. It is working. So she gives a good reward. Okay, this medicine is working, so I'm very happy. Okay, so she gives this good reward and passes it to the model. Model does all its model computation like UCBs and everything. Okay, and gets this yellow model. That is new UCBs. Reward for this green medicine. Now Bob gets this recommendation that okay, let you try this medicine, green medicine. All right, because the model feels that okay, this green medicine is working for some user, so it might be very good. Both has diabetes, so it might be good for him also. Let's suggest it to him. So this has been suggested to Bob. Now, if Bob knows that Alice is the most recent user, but somehow say Bob is the adversary, and he knows, okay, Alice is the most recent user. Then he knows that, okay, after Alice uses the app, it is suggesting me to this thing, this green thing. So his belief that Alice has diabetes has increases. Okay, he now knows that Alice has diabetes. Now think about you can think about, okay, what a bad person can do with this information. Now think about your salary, right? Your salary can get leaked by this similar kind of example or very kind of sensitive data. Think about that way. So this kind of information will reveal a lot of private information. So this is the context is revealing the private information. Okay, so forget about everything. So it turns out you can do all the things like central model, local model, and distributed model in linear bandits also, and get the sweet spot that we're aiming. So let me now don't go much. So all these central model, local model algorithms with lean UCB algorithm you can build. With the interest of time, I just keep everything. This same kind of secure computation you can do, all these things. But the concept is similar for both whatever I've shown you for standard bandits, similar kind of concept will just apply. You need to do a different kind of maths, but it will apply. All right. Okay. I think I should stop here, and there are some resources I need to mention. It's a good book. It's a very good book if you want to know about multi-arm bandits. If you want to know more about UCB and Thompson sampling, these are the links. I think slides will be shared, so you can click on these links and get this. And if you want to know about linear contextual bandit basics, both are very good papers. Differential privacy, this is a book but written by Cynthia Dwork. It's very good, and you can get all the basics and everything. Similarly, DP bandit, this is 2 papers. This is one of our paper, distributed. Contextual bandit, central, local, these are 2 prior work, and this is shuffle, this is our work. And I am trying to get all this. I am not a proficient coder. I try to get all this in GitHub and making it a good package. It's under construction, but you can still check it out. Okay, thank you.
Yeah, so thank you for the wonderful talk. So since unfortunately we have to proceed to to our next thing, and there were already a lot of questions during the talk. So let's skip the Q&A session and
Thank you.